Okay, right. So next question that we're going to go and have a look at, this thing about like rates of reaction, energy profile diagrams, and such forth. There's always loads of marks available for questions that are looking at this. And once you kind of get your head around it, there's various like little things that come up almost every time, right? So the reaction between hydrogen and oxygen releases energy. Right, first thing that you need to think about whenever you're reacting something with oxygen, right, you always need to be thinking, right, that's combustion, right? So the fact that combustion is like burning stuff, we know that burning stuff releases heat, so it's got to be releasing energy. Right, the next thing that you need to be thinking about, if something is releasing energy, then if that's kind of the energy level of your reactants, the energy level of your products is always going to be lower, right? Right, it's got to be lower because that change between the reactants and the products, right, that's the amount of energy that's being given out. So that's why it feels hot or whatever. So we go back to this question then. So student drew a reaction profile for the reaction between hydrogen and oxygen. Right, so figure 1 shows this. Right. It's already told you that it's combustion, effectively. So you should already be looking at this and thinking, the products there have got more energy than the reactants, right? So that's going to be kind of your first error. So the student made 2 errors when drawing this diagram on the reaction profile. Describe these 2 errors. Right, well, for a start, you've got the reactants there, the products there. The products have more energy than the reactants, right? So that's going to be your first error. The second error is that is not showing like where the energy is kind of, it's got the overall energy change. That technically should be energy being given out during the reaction. Another error is that part there where it says overall energy change. Right, that should be energy being released during the reaction and such forth. Right, so there's a few different things. Right, if you remember, effectively, it should have gone and looked something like that. Right. We know that the error can't be in the formulas because we've got, you can go and count up, so we've got 4 hydrogens there, 4 hydrogens there, 2 oxygens there, 2 oxygens there, right, stuff like that. So B, so the reaction between hydrogen and oxygen in a hydrogen fuel cell is used to produce electricity. Excuse me. Right, so hydrogen fuel cells and rechargeable cells are used to power some electric cars. Give 2 advantages of using a hydrogen fuel cell instead of using a rechargeable fuel cell in the car. Right, there's various advantages of it, right? So the first one is that you're only producing water, which isn't particularly harmful. Then you can go on, you can talk about the things that you aren't going to produce. So you're not producing carbon dioxide, you're not producing anything with sulfur in, for instance. If you're going and comparing it to rechargeable things, if you're recharging something, that is going to take a lot longer to do, right? So if you think about a Tesla needs to be plugged in overnight in order to recharge it. This, you just go and you fill it up with hydrogen and such forth, right? So there's all sorts of things. This, because it's not using a battery, is probably going to be a lot more efficient as well. So the next bit on it. So there we go. Right, so this is not what I was looking for. Aha, here we go. So reactions occur at the positive electrode and at the negative electrode of the hydrogen fuel cell. Right, if we're thinking of positive and negative electrode, almost go and think about, right, so it's probably got something to do similar to electrolysis, right? It's always worth thinking. So positive electrode, negative electrode, right? The negative electrode is the cathode. We know it's the cathode because cats are evil. Evil things are negative, therefore cathode, negative electrode, which means the positive electrode is going to be the anode. At the negative electrode, things gain electrons. The positive electrons, things lose, or ions lose electrons. Right, so as soon as you see anything about that positive and negative electrode, that would be the first thing that I would be thinking of. So if you're writing a half equation for one of these reactions, right, if we're writing a half equations involve talking about the electrons, right? So you could go and talk about the hydrogen. So you're going to go with H2. That is going to go and form 2H plus ions plus 2 electrons, right? Because to make that a plus, you'd take an electron away with it, right? So 2 electrons. So that would be one half of it. Right. The other is if you're having O2, for instance, then that would go and, right, you're going to plus 2 electrons to it, give you 2 O minus, right? Now you could go and put it all together, but there's various things. The easiest one to remember is that one where we're looking at the hydrogen. So D. So three-stage symmetric can be represented by a simple particle model. Right, this is somewhere where they're going and they're bringing lots of different parts of the spec and they're putting it into one question. Right, they do this quite often. Right, remember that every 3 or 4 years, everything on the spec needs to be covered in an exam somewhere. So they'll go and they'll try and grasp different bits of the spec and try and put in as much as possible. So this three-stage schematic can be represented by a simple particle model. Right, so figure 2 shows a simple particle model of hydrogen gas. Right, give 2 limitations of this simple particle model. Right, effectively, when we're talking about a limitation, so a limitation, right, realistically means a problem with the model. Right, so you need to be thinking, right, so what isn't that model showing? Right, for a start, it's not showing you how much the particles are vibrating, so how much energy they have. So, no energy shown. Doesn't show you the direction the particles are moving. Doesn't show the speed that the particles are moving at. There's all sorts. It doesn't show you if there's any intermolecular forces in between the particles. It doesn't actually show you, it just says, right, it's hydrogen gas. It doesn't show you that they're going to be molecules of H2, so it doesn't show you the fact that it just puts dot. It doesn't. Instead, realistically, it would be better to go 1 dot, 2 dots, kind of bonded together because it's H2 gas that's moving around, right? So it doesn't actually show you any sort of proper representation of what that gas looks like, right? So there's loads and loads of limitations to it. They go and they put in that question every now and again. There are always limitations, right? So, moving on. So E, so the hydrogen gas needed to power a car for 400 kilometres would occupy a large volume. It's just one way that the volume can be reduced. Right, all that's harking back to is your properties of solids, liquids and gases. Right, so the fact we know that we can pressurise that gas. If we pressurise that gas, you're forcing those gas particles closer together, so you're increasing the pressure, right? That would reduce the volume of it. There's probably a range of other things that you could do. So you could talk about having solids that are impregnated with the gas that release it. You could talk about finding maybe lowering the temperature of the gas so it turns into a liquid. Well, the easiest way to talk about it is just to go compress it more. Right, F. So the energy needed for a car powered by a hydrogen fuel cell to travel 100 kilometres is 58 megajoules. Right? So the energy released from 1 mole of hydrogen gas when it reacts with oxygen is 290 kilojoules. Right? So if you're seeing the phrase megajoule and kilojoule, you need to think there's going to be something there where you're going to need to do some sort of conversion. Right? That's probably the first thing that will be running through my head. So the volume of 1 mole of gas at room temperature is 24 decimeter cubed. Right, that's a number that's worth remembering. 1 mole of any gas at room temperature is 24 decimeter cubed. Right, we'll put it there. 24 decimeter cubed. So calculate the volume of hydrogen gas at room temperature and pressure needed for the car to travel 100 kilometres. Okay, so first thing that you need to probably think about, get everything into the same units. So we know that 58 megajoules is effectively 58,000 kilojoules. Right? So that's the first thing you do. Get everything into the same unit. You could go the opposite way round, I suppose, but yeah, I'd rather not. Right, next you need to go and work out how many moles that you would need, so how many moles of hydrogen you would need. Different colour. Right, so remember, moles equals mass over molar mass. So the number of moles that we're going to need. So we need 58,000 kind of those. So you're going to do 58,000 divided by, go back, and 290, right? Right, next thing you're going to do, so 58, right, can someone just work out 58,000 divided by 290? Oh, I have no calculator. So that is going to equal 200, right, good. Right, so you're going to have 200 moles. Right, next thing you're going to do, because you've got 24 decimeters cubed, so all we're going to do is 200 times that by 24, because you're looking for, that is the volume of 1 mole of hydrogen. We want the volume of 200 moles of hydrogen. So all that, so if you do 200 times 24, so that'd be 4,800 decimeter cubed. Right, so that would be the volume. Right, so we'll just go and run through that again. Like we said, always remember, 1 mole always takes up 24 decimeter cubed. We need to start off by getting everything into the same unit. So we're going to go and turn those megajoules into kilojoules by timesing that 58 by 1,000. So it gives us 58,000. Next, we want to go and work out how many moles of hydrogen. So by doing that, we can see that we're going to need 200 moles of hydrogen gas. Then we know that the volume of 1 mole of hydrogen gas is 24 decimeters. So we're working out the volume of 200. All we're going to do is 200 times by 24. I'll put decimeter cubed there, which gives us 4,800 decimeter cubed. And that would be the volume of hydrogen gas.